Today is going to be one of those lessons where we pull a lot of different pieces together that we've been working with separately and now see how we can integrate them all into one big problem. So at the start here, you see that I'm asking you to solve the equation for x, and I've given you a graphing grid. For this problem, what I'd like you to do is to start by making the graph of that particular equation and then using that to be able to solve it. As usual with these video lessons, try doing it on your own first, pause the video, and then resume it after you've had a chance to process this through and really get an idea about what's going on, and hopefully even complete it. All right, so taking a look at this, first of all, in order to be able to solve it by graphing, we really have two separate equations that we'd want to be looking at the graphs. Our first equation would be y equals 2 to the power of x minus 3. The second equation would just be y equals 5. I'm going to be focusing mainly on the exponential here because that, of course, is our new part that we've just been learning about. So we're going to graph that, and then we're going to look see when does that hit a y value of 5. So remembering how to graph this type of an equation here, we have an exponential, so we know the general shape is going to be something that's doing one of these kinds of things. But it's also got that minus 3 hanging on the end. Now that minus 3 moves it down 3. Please make sure that you start by actually drawing in the asymptote, because of course, if it was just 2 to the power of x, our asymptote would be there at 0. That would just be plain old 2 to the power of x. But the minus 3, that means that this whole thing has been shifted down 3. So start by drawing in your asymptote there, and then we draw a graph that goes from there. So our first point, it always goes up 1 from the asymptote. In this case, it's not been moved over at all. So when it's up 1, it's right on the y-axis. Then from there, the fact that it's 2 to the power of x means we're going to be doubling our height. Now, if there's anything that's tending to give people trouble on these graphs right now, it's that we know, okay, I got to go up 2. But I'm seeing a lot of you want to go over 1 and up 2 from the first point, which makes sense, honestly, because that's the way all of our other graphs have been. We've always looked at the starting point and always counted from the starting point. We don't with the exponentials, though. That's because our starting point isn't at 0 normally. Our starting point's normally at 1. We always want to count from 0. In this case, that's where the asymptote is. So when I count up 2, I'm counting up 2 from the asymptote. So then that's going to be the location of my next point. And then so if that one is currently up 2, then my next one's going to have to be up twice that, which is going to be up 4. And then if that one's up 4, then the next one needs to be up twice as far as that, which is 8. That's all I can fit on the right-hand side, because if that's up 8, the next one would have to be up 16, and that's going to be up here off my graphing grid, so I'm not going to worry about that one. But I do want to worry about plotting some points on the left-hand side, because I want to be precise. Otherwise, if we try to draw this curve in as we see it here, we might just do that, which might be good, or we might do something where we just get right down on, and there's small differences, I know, as we're looking at these points here, but I do want to be as precise as I can be. So when we went to the right, remember we multiplied by 2. So that means that as I go to the left, I'm going to divide the height by 2. They're all going to be half as tall as the last point. So then I'm going to have a point over to the left 1. That one is up a half. And then if I go left 1 from there, it's going to be up half as far as that. Half of a half is a fourth. Now, that's going to be enough points, I think, for us to be able to get a nice curve in. So go ahead and draw the curve through those points. And now that we've done that, let's return back to our original problem here, where we're looking to see where does 2 to the power of x minus 3 equal 5? Well, if I now went and drew in the equation for y equals 5, that would just be a horizontal line up here at 5. And my answer then is where they cross. So you notice they cross right at that point. So they cross at that point where x equals, and notice I want to give the x because x is the only variable in there, and that's what we're being asked to solve for, 3. So x equals 3 in this case. So we could actually solve this sort of equation by graphing. Now that's great, as long as we have a problem like this where we can just look at our graph and see where that point of intersection occurs. But sometimes they get a little bit more complicated. Like if you take a look at this one, notice I left the left-hand side the same, but on the right-hand side, it's no longer equal to 5. This time I want to see, okay, when does that same one equal 9? Well, if I go back to my graph and consult it, that means I'd be looking to see where does this graph cross 9 here. And so I can see the point on my graph, but that doesn't necessarily help me to know the answer here because it looks like it's maybe like 3.5-ish. It's kind of hard to tell exactly where, and we don't know if that would be exactly 3.5 or a little bit off from it. So we're going to need some other way to be able to solve this equation. Now, this isn't going to be an algebraic method, and it will actually be able to tell us a decimal solution. So expected decimal, I'll go ahead and tell you right now that we're going to round our answer to the nearest hundredth. All right, let's start solving this through. Again, algebraically. This is why we've been doing some of our work with inverses with these. Basically, use all the same skills you know for how to find the inverse of an exponential to solve the exponential here. So if you're looking at this one with that inverse mindset, I would hope that you would be saying, well, the first thing I need to do is I need to move this -3 out of the left-hand side, and I need to move it over to the right. So I'm going to add 3 to both sides of my equation. Having done that, I now have my exponential by itself on the left-hand side. So now I'm going to solve that for x. So that is, I'm going to try to turn this exponential into a logarithm. And so we end up with x equals log base 2 of 12. Now it's a matter of, okay, now how do I actually calculate that as a value? So again, going back to some work from way earlier this year, we saw how we could calculate a log value like this. Please remember, this is not just, I cannot just type it in my calculator as log 2 times 12. I see some people try that. It's not the same thing. That's log base 10 of 2. Remember, that's what that log of 2 really means. That's log base 10 of 2 and taking that answer and multiplying it by 12. Very different from what this is asking us to figure out. This is what is log base 2 of 12. That is 2 to the power of what is 12. So we use change of base formula in order to be able to figure this out. Change of base formula, that's the one where we do log divided by log. Yes, you will have to know change of base formula very well in this unit. So I do log divided by log, and a nice way to remember is that the number that gets written lower like that goes on the bottom of your fraction. All right, so now we know that in order to be able to calculate this value, we are going to be doing log 12 divided by log of 2. Now it's calculator work. Go ahead and plug that into your calculator, and you should get an answer of about 3.58 when rounded to the nearest hundredth. That problem then is done. And this is our basic idea behind solving an exponential equation algebraically. This was your first example, and we're just going to do one other example here together because you've been doing all this other work already, just in different little forms and different pieces. I think we can go ahead and go straight into something that's way more complicated, like this. This is about as complicated as you're going to see. It's got everything in it, but the same principles are going to apply here. So because I think you already kind of have the idea about how to approach this, again, write this problem down and then try to work it on your own first. So go ahead and pause the recording, go work it, and then come back. All right, so if I'm going to be able to solve this one for x, think when we did our inverses, we had to get the exponential part by itself first, and that's going to be no different here. So I got the 2 that's multiplied there, and I got the -8 that's there. Since I'm trying to solve this equation, I'm having to undo it, so I'm going backwards through the order of operations. So the very first thing I'm going to do is I'm going to move out that -8, and then I'm going to get rid of the 2 from both sides. So if I'm going to move that -8 out of the left, that means I'm going to have to undo subtracting 8, so I'm going to add 8 to both sides there. Having done that, I now can go ahead and get rid of the 2. Since it's currently 2 times my exponential, I'm going to get rid of it by dividing by 2. And so that now leaves us with our exponential. We have 3 to the power of x minus 1 equals 64. And just like we did when we were finding our inverses, in order to solve for the exponent, I'm going to turn this into logarithmic form. So if I write it as a log, I end up getting x minus 1 equals log base 3 of 64. Now, if you wrote this the other way, if you wrote the log base 3 of 64 on the left-hand side, and the x minus 1 on the right-hand side, that's perfectly fine. There's nothing magical about what goes on which side when doing this. All right, now looking at this, you might be tempted at this point to say, okay, now I'm going to go ahead and just add the 1 to both sides. But if you did that, where would you be adding the 1 on the right-hand side? We cannot add the 64 and the 1 because that 64 is trapped inside the logarithm. And we certainly can't add the 3 and the 1 because the 3 is the base of our logarithm. It's also trapped with that logarithm. So really there's nothing I can do with that plus 1 at the moment. So instead, I'm going to make the right side into something that I can work with. I'm going to make the right side into a number, which means calculating out what does log base 3 of 64 equal. That, of course, means using the change of base formula. So I'm going to be doing log 64 divided by log of 3. And again, then that's calculator work. So we do log 64, get that value, divide it by log of 3, and we get about 3.78. Now this is a never-ending decimal right now. Keep that decimal showing on your calculator after doing that calculation, because since we have more calculations to do, we don't want to run into the risk of having any rounding error along the way. All right, so now with that number still showing on your calculator, we can now add the 1 to both sides. So you just say plus 1. Of course, all that does is change the whole number out front. But that then gives us our final answer, and then I can go ahead and round my final answer to the nearest hundredth at this point. You'll notice up here I wrote 3.78 and then just 3 dots. I just wanted to keep track of what kind of number that was, 3.78, and it's a never-ending decimal while it was showing on my calculator. Notice my 8 became a 9 in the final answer because it did round up. I know that because I looked at my calculator to see that value. There was nothing about what I wrote here that told me that. It was all about using that whole number in the calculator.